Welcome back to my YouTube channel all about VLSI. In our previous videos, we have seen about Ethernet frame and we have started with Ethernet frame discussion where we were having preamble, destination MAC address, source MAC address, and type, field, the data, and FCS. We have discussed about this preamble, destination, source, type, and data and all. Now, let us try to understand about what do you mean by frame check sequence. Now, basically, this frame check sequence is used for parity, and this frame check sequence field basically it is going to use something known as CRC. CRC is nothing but Cyclic Redundancy Check, and the purpose of this is for error detection. And the significance is the receiver it is going to recalculate the CRC, and if it is matching, then we are going to accept the frame, or if it is not matching, we are dropping the frame. Now, what do I mean by matching and what do I mean by not matching? Let us try to understand. Now, let's say if I'm going to, first of all, let's see the steps for how we are going to perform CRC. So, step number one is we need to, first of all, define the inputs. So, let's say if I'm going to have a data message as 1101011011, and I'm going to have some kind of polynomial in this particular CRC calculations. So, in the CRC calculations, let's say this is my polynomial which is 10011. So it is equivalent to x power 4 x power 4 plus x power 1 plus x power 0, since this coefficients are equal to 1 and remaining all power coefficients are equal to 0. That's the reason this is nothing but my CRC polynomial x power 4 plus x plus 1. Now, after having the polynomial in the sender side, I'm talking about the sender side. So after having the polynomial, I'm going to have the polynomial that is my generated polynomial. I'm going to append four number of zeros with my data. Why four number of zeros? You need to decide the number of zeros you want to append to your data depending upon the degree. So here the highest power degree is 4, so that I'm going to append four number of zeros with my actual data, and I'm going to perform modular division with my polynomial or generated polynomial. So let's try to understand how we are going to perform this particular process. Let's say if I'm going to have a data, let's say my data over here is, which data should I take? Yeah, let's take 1010. This is my data. 1010 is my data. And let's say my generator polynomial, which I am going to consider, generator polynomial, which I'm going to consider over here is 110101. This is my generator polynomial, which I'm going to consider. And this is nothing but x power 5 plus x power 4, x power 3 coefficient is equal to 0, x power 2, x power 1 coefficient is equal to 0 plus 1. So this is the generator polynomial which I'm going to consider. Now I'm going to perform modular division between 1010 and 110101. And before that I'm going to add 5 number of zeros, since the highest power degree is equal to 5. So to my data I'm going to add 5 number of zeros. So let's see how to write it down. 1010 followed by 1, 2, 3, 4, and 5. Like this, I'm going to have 5 number of zeros, and my generated polynomial here is 110101. 110101. Now I'm going to perform XOR operation between this and this numbers. So which is nothing but 110101. So this is a polynomial which I'm going to have. Now, if I perform XOR operation, it is 1, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, and 0 XOR 1 is 1, and 1 XOR 1 is 0. I need to consider the bits from 1, not 0. I need to consider the bits from 1. So this is 1, 2, 3, 4, 5, and I need to take one more bit from here, and again I need to perform XOR operation between this two, 110, 101. So my resultant is basically 1, 10 is 1, 01 is 1, 10 is 1. And 1 XOR 1 is 0, 1 XOR 1 is equal to 0. So I have 1, 2, 3, 4 bits only. So I'm going to take 2 more bits, 0, 0. So total 1, 2, 3, 4, 5, 6. And again I need to perform XOR operation between this two, 110, 101. So what is that I'm going to get? 0 XOR 1 is 1, 0 XOR 0 is 0, 1 XOR 1 is 0, 1 XOR 0 is 1, and 0, 0. So this is what I'm going to get, 1, 2, 3, 4, 5. So this 5 bits I'm going to append with my original data 1010. So the sender is going to send the data 1010 followed by 01001. This is the data my sender is going to send to my receiver. Receiver, after going to receive this particular data which was appended with the redundant bits, it is going to again perform modulo division. So how it is going to perform modulo division? So let's check it out. So let's say my sender is receiving the data 1010 01001 01001. This is my sender, which it is being receiving. Right now, it is going to again perform modular division, and it is going to have the same polynomial 110101. So we are going to perform the XOR operation 110101. So what is that result we are going to get? 1 XOR 1 is 0. 0 XOR with 0 0 1 1 1 triple 100 we are going to get, which is 1 2 3 4 5, and we need to take one more 0 over here. Now again, if we perform XOR operation 110 101. So what is that? I'm going to get 0 XOR 1 is 1 0 0 XOR 1 is 1 1 XOR with 0 is 1, and 0 followed by 0. Okay, so 1 2 3 4, and I'm going to take two more zeros from here. I mean two more bits from here, and if I again perform XOR operation between them, what is that I'm going to get? Remainder is 0, because everything is same, right? So I'm going to get the remainder as 0. That means whatever the data which I have received is a valid data. If I'm going to get the remainder is equal to 0, that means whatever the data which I have got is a valid data. If my remainder is not equal to 0, that means whatever the data which I have received is not a valid data. Now, this particular operation we need to perform using the hardware. Using the hardware, how we are going to perform the operation, let us try to understand. Now, we are going to consider few steps for performing this particular operation using the hardware. So step number one is we are going to, so these are the steps. So step number one is we need to take the polynomial. Over here, the exam, we are going to take 110101, where this is the polynomial x power 5, x power 4, x power 2 plus 1. Now, after that, we need to find the CRC bit. So highest power is 5, right? So we are going to use 5 flip-flops. So since the highest power we are going to have is x power 5, we are going to use 5 number of flip-flops. And this is first flip-flop, second, third, fourth, and fifth. So this is my first flip-flop, and this is my fifth flip-flop. And Q0 to Q4. Now after that, I'm going to ignore my MSB bit temporarily. So I'm going to have 110101, right? So this from here I'm going to consider. So these are my flip-flops. X power 4, X power 3, X power 2, X power 1, X power 0 is nothing but, sorry, I mean over here 110101 I'm going to have from here, right? Now what I'm going to do, and these are my flip-flops, 1, 2, 3, 4, 5 flip-flops, and X power 5 I'm going to uh, temporarily skip or ignore for now. Okay. Now, highest term is x power 5, and it is only used to tell me the number of stages. Now, after that, the remaining bits are used. That is, Q4 is basically 1. You can see from here, x power 4 is nothing but Q4. I have told you, right? Q4 is nothing but x power 4. And x power 3 is basically 0, which is Q3, considered as the second flip-flop. Next, x power 2 is considered as the third flip-flop. X power 1 is considered as the fourth flip-flop, and x power 0 is considered as the fifth flip-flop, that is LSB. So this is my LSB flip-flop, and this is my MSB flip-flop. So total 5 flip-flops. I am not going to consider the x power 5. I'm not going to consider, I'm only going to consider the coefficients from x power 4 to x power 0, where x power 0 is the LSB flip-flop and x power 4 is the MSB flip-flop. So that your diagram is going to look like this. Okay, so we have took 1, this is Q0, Q1, Q2, Q3, Q4. Now, if you carefully observe, we have XOR gate connections with us. So we are having some XOR gate connections. Q0 is, if you want to get Q0, it is being fed from this XOR gate. The input of this particular flip-flop is fed from the XOR gate. And if we want to get Q2, the input of this flip-flop is fed from the XOR gate. And if we want Q4, the input of this flip-flop is fed with the XOR gate. So how we are going to decide which particular flip-flop is fed with the XOR gate is we are going to look for this particular coefficients. So here we are having the data as 1 0 1 0 1, which is nothing but x power 4 is having the coefficient as 1. X power 3 is not having the coefficient as 0. I mean, x power 3 is not having the coefficient as 1, and x power 2 is having the coefficient as 1. X power 1 is not having the coefficient as 1, and x power 0 is having the coefficient as 1. So over here, x power 4 is nothing but q4, q2, q1. I mean q0. So q4 is going to have the XOR gate connection. Q2 is also going to have the XOR gate, and Q0 is also going to have the XOR gate, and these are known as taps. So whatever the flip-flops or whatever the coefficients we are going to have as one, for that we are going to provide the tap connections or XOR gate connections. So you can see from the diagram also, Q4 is having the tap connection, Q2 is having the tap connection, and Q0 is having the tap connection. And before going to give the input to my first LSB, I'm going to provide the input data in with Q4 XORed. So Q4 and data in are being XORed, and it is given to my first flip-flop and also this particular XOR gate. So this is nothing but my feedback. So whatever the data, whatever my Q4 as well as my Q1. So Q1 XOR with data in XOR with my Q1. That is what I'm going to give it to my this particular flip-flop. And this flip-flop also I'm going to perform the XOR operation between them and with the Q3. This I'm going to give it to my this particular flip-flop. Like this, I'm going to decide which particular flip-flop is going to have the XOR connection. Now let us try to verify this particular diagram, and over here it is a serial data. So we are going to provide serial data one by one. We are going to provide it over here. Now let us try to understand whether it is working correctly or not. Now let's say what is the data which we have took over here. The data which we have took for our calculation was 1010 is our data. So I'm going to consider the data which I'm going to give over to my design is 1010. This is my data which I'm going to provide. And what is the polynomial which we have from the diagram also we can see the we can get the polynomial. For this Q4 we are having the tab, so we are going to have 1, and for Q3 there is no tab, so it is 0, and Q2 we have the tab, it is 1, and Q1 and Q2 we had the tab, that's why we have written, and Q1 is not having any tab, 0, and Q0 is having the tab, 1, and MSB is always 1 because it's a highest degrees always should be equal to 1. X power 5 is 1. Okay, so that is how we are going to write down the polynomial directly by seeing the diagram also. Now this is my polynomial 110101. So I don't need the polynomial now, so I need the data which I want to give. So Q4, Q3, Q2, Q1, and Q0. And this is my feedback, and this is my input. So let's say the content of Q4, Q3, Q2, Q1, Q0 are equal to 0. And let's say I'm going to provide the input as 1. This is the first input I'm going to provide. So what is the feedback? Feedback is this line. So what is the feedback I'm going to get? Q4 XOR with data. So which is nothing but Q4 XOR with data. Sorry, Q4 XOR with data is nothing but feedback is equal to 1. Now, this is my first cycle. In the second cycle, what is going to happen? What is the value of Q0? Q0 is nothing but feedback. Feedback is Q4 XOR with data. So, which is equal to 1. So, I'm going to have 1 present over here. And what is Q1? Q1 is nothing but right left shift of your Q0. Okay. So, Q1 is nothing but 0. And what about your Q2? Q2 is nothing but Q1 XOR with feedback. So, what is your Q1? Q1 is 0. XOR with feedback is 1. So Q2 will be equal to 1. And what about your Q3? Q3 is nothing but shifted version of Q2, which is equal to 0. And what about your Q4? Q4 is nothing but Q3 XOR with feedback. So Q3 XOR with feedback is equal to 1. So this is the content of my register at the second clock cycle. Now I'm going to provide the second data item, which is 0. So if I'm going to provide 0, my feedback will be again 1 because input XOR with Q4 is nothing but my feedback, which is equal to 1. That will be given to my Q0, and Q1 I can see from the diagram, it is shifted version, and Q2 is nothing but Q1 XOR with my feedback, which is again 1, and Q3 is nothing but shifted version of Q2, and Q4 is nothing but Q3 XOR with my feedback, which is again 1. So this is my register content which I'm going to get. Now, next is another input is 1. So here input is equal to 1 at the third cycle. We are going to give the input as 1, then the feedback will be equal to 0 because Q4 XOR with 1 is nothing but 0. So this 0 will be given to Q0. Q1 is nothing but shifted version of Q0 and Q2 is nothing but Q1 XOR with feedback, which is again 1, and Q3 is nothing but shifted version of Q2 and Q4 is nothing but Q3 XOR with feedback, which is again 1. So this is the content of fourth cycle. Now at the fifth cycle, what is that we are going to get? We are going to give the input as 0. This is the last input which we are going to give. And again, the feedback is equal to 1. So this will be given to my Q0 and this will be left shifted. And my Q2 is nothing but Q1 XOR with feedback, which is again 0. And Q3 is shifted version of Q2 and Q4 is nothing but 1 XOR with 1 is nothing but 0. So this is what I'm going to get 1001. So this is the CRC, that is my reminder, which is the appended or redundant bit which I'm going to have. This particular bit, this particular value will be stored inside your register as 1001. And this we are going to take it from this particular register and we are going to append with our the original data. Now, this is how we are going to perform the CRC calculation. But if you have carefully observed, we were having 4 data items that we need to pass them serially, and we need some cycles to get our actual result, which we want to append with our original data. That is my redundant bit. Now, that's the reason this particular method we are not going to follow for actual CRC calculation, because in CRC 32 we are going to have 32-bit polynomial. That means we are going to have 32-bit registers. So in that case, we are going to use another trick, and using that trick only we are going to develop our Verilog coding. This is for just basic understanding of how CRC works. Okay. Yes, so that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.